Assalamualaikum and good day. Today we're going to continue with the last part of chapter 4, pulse modulation. So we're going to start with this delta modulations. Okay. So delta modulation is different kinds of modulation than what you have learned in the other pulse code modulation. So in sense that here we only use a single bit. Okay, we only use single bit PCM, which is either 0 or 1, but only single bit. And the B used is to indicate whether the current sample is smaller or larger than the previous one. Only that. So if you see here, okay, if you see here, this means logic 0 if the current sample is smaller, and logic 1 if the current sample is larger. So it's basically like, okay, you see here, ping 1 is our information signals, and this one is our sample signal. So if you can see, as it goes down, okay, we will shown as system will show as 0, 0, 0. And if the current sampling, current information signal going up, the sampling going up, so means it's larger. So you're going to have 1, 1, 1, 1. Okay. And if it goes down, you're going to have 0, 0, 0, 0 again. Okay. So this is pretty much what is delta modulation. So when you have when you are using delta modulation, so you're going to have this kind like this may happen where effect of a steep slope. So this can contribute to the noise, means the disadvantage of this system. Okay. So conventional PCM uses a much higher bit, typically at compared to delta modulation 1 bit. So the advantage of this data modulation is less complicated. Okay, where we only need to use 1 bit. However, you can see maybe much this one you will have more information because we will have more bits. The other methods. So this is one of the, so this can be the disadvantage of data modulation. So you see here, however, the M suffer from slot overload noise. Okay, if a consecutive of or a string of 1 or 0, so if you keep continue to have 1 or 0, okay, then you will see that the slope of the output to digital analog to digital converter output is less than the slope of the analog signal. So this is ADC. Where you have the changes of analog to your digital. Okay, so sampling, quantization, and coding. Okay. So with a consecutive of string or ones or zero, slope of ADC output is less than slope of the analog signal. This is where you can see from the previous slides. So you can see, okay, if we have continue to have continue of strings of ones, okay, then we have going to have slope overload noise, because this is a continuous zeros like this. So we're going to have a slope of noise. So similarly, if we have continuous slope of 1, okay, so slope of ADC output is less than slope of the analog signal. Okay, meaning to say this slope is less than the slope of our information signal, the analog signal. Okay, so we need to address this issue. In order to address this issue, we in this DM data modulation, so to overcome that is the additive DM, additive data modulation is proposed. Okay, so step size is automatically reduced or increased depending on the amplitude of the analog signal. So if there is changes, okay, if there is changes in the information signals based on the amplitude, the step size, okay, the step size will be vary. Okay, the step size will be very so that to catch up to this changes. Okay, the step size is increased until the output catches up to the analog signals. When alternative sequence of 1 or 0 occurs, it goes back to the minimum step size. So when it changes back, okay, when it changes back to, for example, if you have 0 0 0 0 0, okay, then there will be like adaptive, okay, mode here where the step size is varied. Okay, but once it have 0 means when from 1 change to 0 or 0 change to 1, so we will going to have a minimum initial step size. Okay, so if you see here, okay, this is your information signal and this is your sampling. Okay, if you can see, uh, slope is increased. Okay, the slope is increased if you may, if you want to measure the gradients, okay, you can see the gradient will increase. So when this one is the original analog is increased, the step size of our data modulation will be also increased accordingly. Means this one, that's why is adaptive. Okay, means our step size will not be fixed. And if you see that increase, and then when you see it going to change back, okay, then you can see that the step size is changed accordingly. Okay, when this one is the slope overload is reduced. Okay, so you can see that the difference, okay, the difference is reduced rather than if we use constant step size, uniform step size, then we will have a bigger slope overload noise. So this one is basically reduced. We want to make it closer to these original signals. Okay, so that's why we use a varying step size. Okay, and then here is the granular noise is minimized. Okay, when the slope of the input signal is greater, okay, this one is greater than the slope of the output, slope overload can be avoided by increasing the step size or sampling frequency. So here what we basically do, granular noise is the fluctuation effect due to decrease or increase in the step size, more obvious for the flat signal. So this one is your flat signal. Okay, so you will have granular noise. Granular noise, however, it is minimized in the data modulations. Okay, so if you can see, the fluctuation effect due to the increase in the step size is reduced. So if you use adaptive data modulations. Okay, so this one is actually for the flat signal. Okay, when we talk about this flat signal, is we tends to have granular noise. Okay, so this one you can try at home. Okay, you can try at home. This one I take from other lecturers. Okay, Dr. Nadia Huda. So if we PCM signal is produced using a non-uniform quantization where the compressing parameter mu law. So means this one is we are using mu law. Okay. So if the common mu law, if I'm not mistaken, is 255. Okay. So now it's 70. So determine the number of quantization levels. Okay. It means how many L if the minimum SNR is equal to 40 dB. Okay. So basically this question is on the non-uniform quantizations. Okay. And it given you the value. This one is normally given. Okay. So a baseband signal in the form of a square wave with frequency of 10 kHz need to be sampled. So you're going to have a baseband signal means information signal. Okay. In the form of square wave mean this one is your information signal. So with a frequency of 10, sorry, square wave. So you're going to have square wave. Okay, depending on how the square wave. Okay, the amplitude, whatever. Okay, with a frequency of 10, what is the sampling frequency if the signal is sampled up to the third harmonic? Give reason. what is the sampling frequency if the signal is sampled up to the third. Okay, so what is FS here? Okay, remember the Nyquist rate. Okay, so what signal will be recovered if the base signal is sampled at 25 samples per second and 1000 Ka sample per second. Okay. So the next one is an analog signal is limited to an amplitude range of 0 to 5 volts. So you're going to have V peak to peak equals to 5 volt only. Okay. Calculate quantization interval when digitized with 4 bits and 8 bits per sample. So here n is equals to 4 and n is equal to n. Okay, so what is the quantization interval? So what is the quantization interval here? Sketch the quantization level for the 4-bit quantization. So basically you just need to sketch the quantizations level that you're going to have for the given n. Okay, sketch the form of the digital signal for the 5 volt, 1 volt, and 2.5 volt for 4-bit quantization. So means they give you n equals to 4 system. So means you're going to have 2 to the power of n equals to 4. 2 to 4 is you're going to have 16. Okay, you're going to have 16 quantization level. So what is the digital signal? What is the corresponding digital signal for this digital signal? So for example, this given 5 volt, what is the equivalent? Maybe 1001. But because this is 4-bit quantization, so 2n to 4 16. So you should have 16 numbers, 16 binary numbers. What voltage do the following digit sample represent? Okay, so 1000, 0110, 100, 1110. Okay. So this one is for analog for 0 to 5 volts. Okay, what voltage do the following digital sample represent? So this one basically is how many sorry, this one is not 6 wait, this one is 2 4 16 interval 16 quantization level, but 4 bits only. Okay, I am sorry, a bit. Okay, so means non-uniform quantization. For example 000, okay, 001. So this is in terms of 4-bit numbers, but you will have a 16 quantization level. Okay, so discuss the effect of quantization error for an 8-bit sample. Okay, so this one you need to see to test your understanding. Okay, so the next one is the line coding. Okay, this is the final part of this chapter. And the next one you will going to have this RZ, not RZ. Okay, never mind, we continue. So line coding is a binary 1 and 0 in PCM signal can be represented by several formats known as line coding. So what you have is that first, just now, you have your information signals. Okay, you have your information signal. Then you have your PCM. Okay, then you have your pulse code modulations, and you go after this with the next stage you should do is line coder. Okay, line coding. Okay, before you go to the channel. So consideration for line coding formats, okay, is transmission voltage and level, duty cycle, bandwidth, synchronization, error detection, and correction. So this is consideration for the format of line coding. Sorry. So transmission voltage or level. So whether this one is unipolar or bipolar. So if you have unipolar, so you only have only one side like this 5 volts. If you have bipolar, you're going to have positive and negative here. So this unipolar or bipolar will affect the power efficiency. Okay. The duty cycle is the ratio of the active bit time over bit period. This one is a bit like when you learn in digital electronic, we call it duty cycle. I forget duty period, whatever. So this one is the active bit, okay, over the bit period. So uh, how many ones do you have over the total bits period? Okay, so this one is the active bit, okay, where you have active bit over a given period. So in the non-written zero, it is 100%. It is 100% duty cycle. So we will learn this later on. Okay, so bandwidth requirements depend on the transition of bit sequence. Okay, so this is you transmit multiple stream of you transmit a stream of bits. Okay, so this one is there will be a transition on the bit sequence. So this is what determines the bandwidth. Okay, uh depends sorry determines the bandwidth. Okay, not directly, okay, but it's actually this depend on this transition. The bandwidth is depend on the transition of the bit sequence. So there is a if there is a transition, highest fundamental frequency, okay, of nRZ non-return to zero is half of RZ return to zero. So if you can see for the bandwidth requirement, okay, the highest fundamental frequency for this nRZ is half of your RZ. Okay, so this one is actually we will learn about this later on. Okay, later on. Okay, just that for your overview. Okay, so the nRZ for this fundamental frequency f not nRZ is actually half equals to half of not RZ. Okay, synchronization, for synchronization purpose, enough transition is needed. Okay, so this one is for it to be synchronized. Okay, long streets of 0 or 1 would be inadequate. Okay, bipolar RZ, okay, in terms of synchronization, bipolar return 0 has a good synchronization. So we need to consider here, okay, which for which line coding format that we will be using based on this criteria. Depends on what we need. Okay, for example, if the question asks you, okay, what line coding format would suit the best if the synchronization is a priority. Okay, if synchronization is a priority, so then the answer will be bipolar RZ. Okay, it's not RZ but bipolar RZ. Next is error detection and correction. So where we have ability to detect error, okay, we not just stop there. We need to correct for the errors. So for the system to be to be reliable, okay, it needs to be able to detect errors and also to correct them. Okay, the coding provide mechanism for error detection or coding. So which doesn't have in the unipolar RZ, okay, and NRZ did not have these capabilities. Okay, RZ-AMI has built-in error detection mechanism. So return 0, AMI, we will learn later. Okay, have this error detection mechanism. So this is the overview, so that when you go through after this, you will relate them. Okay, so this is the line coding formats. Okay, line coding formats. So you have, if you refer to, you can refer to the module. Okay, you refer to module. It is actually in page 131. Okay, where we start to have this channel coding. Okay, line coding. Okay, so here is UP is unipolar, and this one is none return to zero. This one is BP bipolar, none return to zero. This one is unipolar, return zero. Bipolar, return zero. And BP RZ. Okay, this is bipolar, return zero. Okay, so in the books, you have a good illustration there. Okay, you can look at there. Okay, so if you see here, fastest transition of voltage cycles. Okay, if you see the you see bipolar NRZ, so the bandwidth is FB over 2. Okay, the bandwidth is FB over 2. For bipolar NRZ, the bandwidth is still the same. Okay, even though it's a bipolar, so it's the bandwidth is still maintained. For the return to zero, okay, if you see regardless of unipolar or bipolar, so the bandwidth is equals to FB. Okay? So BPRZ MI, the bandwidth is FB over 2. Okay, so let's go to this example for the unipolar non-return to zero. What does it mean unipolar? So you only have one polarity. So here is 0 to 0 to positive volt only. Okay, so you're not going to have negative. It's either all positive or either all negative. Means only one sign. So here, this is the non-return to zero. Okay. Okay, we will, if you see here, okay, so the shape is the same regardless whether it is unipolar or bipolar. The difference is that it's just that the magnitude, okay, the magnitude is, okay. So here, for example, here is 5 volts. Okay, they say here is 5 volts. So here will be to the positive side is will be positive 5 volts, and here will be negative 5 volts. Negative 5 volts. So it's the peak to peak still maintained. It's just that the polarity used. Okay. So here is your 1 1. Okay, and then 0 0 0 1 and 0. Okay. So this is the fundamental frequency. Okay, highest fundamental frequency. So you know how to do fundamental frequency. It's just the 1 over TB. 1 over T. Okay, so this one is unipolar return to zero. Okay, unipolar return to zero. Okay, sorry, sorry. Okay, this one is unipolar return to zero. So you see here in the module for the non-return to zero first. Okay, for the page 131. Okay, NRZ code format is simple code to implemented. As the name implies, this code does not return to zero for each bit interval. So this one is a bit interval. Okay, you can see there is no return to 1, so it's just proceeds. Okay, it's not does not return to value 0, so non return to 0, so it's no return, so it's just proceeds. Okay, and then here also just proceed. Okay, after each bit interval, this one is bit interval. Okay, so the same also go for the bipolar. So next is your return to zero. Return to zero is actually if you see it from the slides, okay, it will go back to value 0 for each of the clock cycle. So this is clock cycle. So if you have this, okay, here for given one, okay, so it will return to 0. Okay, it will return to 0 for each clock cycle. So if you see, there is in the books, we have three types of return to 0, okay, which is the RZ unipolar, okay, this one. And then the next is we have return to 0 bipolar RZ. Then the next one is the alternate mark inversion. So this one is an alternate mark inversion. So return to 0, okay, means all of them should return to 0 for each of this bit cycle. So we see first for this unipolar return to 0. So the positive pulse that return to 0 before the end of bit interval here. You can see, right? It return to 0 before the end of bit interval. And for value of 0, for the unipolar RZ, you're going to have absence of pulse. So this one will be no pulse here, okay, for the bit of 0. Okay, for the return to 0 bipolar, okay, the positive pulse, okay, the positive will return to 0 before end of bit interval. You can see it return to 0 before the end of the bit interval. So this is your bit interval. Okay, for the 0, okay, for the 0, however, this one is 0. So negative pulse will the return 0 here. You will going to have, okay, go to negative and goes back to 0. So this one is for the bipolar RZ. So difference in the bipolar, in the unipolar RZ, the 0 is just absence of pulse. So just like a straight line with 0 as the minimum, because this one is unipolar. But for the bipolar RZ, for the 0, we're going to have the slope going down here to the negative amplitudes, and then need to return back to 0 for each bits interval before end of bit interval. So the next one is the return to 0 alternate mark inversions. This one is a bipolar RZ. So you're going to have positive and you're going to have negative. So for the alternate mark inversion, for the bit 1, okay, for the bit 1 here, so positive and negative pulses of equal amplitude are used alternately. Okay. So if you see here, for this AMI, okay, for the bit 1, okay, for the first, okay, what does it mean by they use alternately? So for the bit 1, you can see this one is using the positive amplitude, and for sure it's written to 0 afterwards because this is RZ anyway. And after that, for the next one, it will alternate, means this one is positive, so the next one will be negative. And for the bit 0 is we just absent of pulse. Okay, and the next bit is 1. So before this we have negative amplitude, so the next representation for 1 will be a positive here. Okay. Then 0 will be absence of pulse, and this one for bit 1 is alternate. Okay. Since this one you have using this positive is negative, and then for the 0 bits is just the absence of pulse. Okay. So this is the comparison. Okay, the comparison So this one is the comparisons between the unipolar, non-return to zero, bipolar, non-return to zero, unipolar return zero, bipolar return zero, bipolar return to zero, AMI. So this one is we're going to have only one sign, and bipolar we're going to have positive, negative. This one positive, this one is positive, negative, bipolar, and this one is positive, negative. Alternate mark, alternate mark inversions. Okay. So for the minimum bandwidth, UP NRZ will require bandwidth minimum FB over 2. Okay. And bipolar non-return to zero as well, regardless it's unipolar or bipolar. So it still requires FB over 2. For the return to zero, we're going to have FB and B RZ also RZ also the same regardless of unipolar or bipolar. So you can see that this RZ consume more bandwidth. Okay, so which is maybe in terms of bandwidth we prefer those with FB over 2. Okay, so similarly PPRZ AMI however have the half of the bandwidth requirement compared to this his siblings for the unipolar RZ and bipolar RZ. For BPRZ MI require half the bandwidth. So the average DC value, okay, the average DC value for the UP and RZ is V over 2, okay, because we're only going to use is V over 2, okay, unipolar, okay, V over 2, this average DC value. For the bipolar non-return to zero, so it will be 0 because you take for example positive 5 volt and negative 5 volt, right? So it should be like a 0. And then for the unipolar RZs, the average DC is V over 4, bipolar RZ 0, and bipolar RZ AMI is 0. Okay, so for the clock recovery, okay, clock recovery, UP NRZs, okay, for the NRZ, so it's have a poor recovery, and for the return zero, it will have a good clock recovery. So in terms of the, this one is in terms of the clock lah, okay, so BPRZ have the best clock recovery, and BPRZ MI have a good, okay, recovery. In terms of clock recovery, BPRZ give the best one, okay. So bipolar return 0. Okay. For the error detection, all of the line coding formats, okay, have no ability for error detections except for this alternate mark inversions. Okay. So in overall, okay, BPRZ AMI will have the best overall quality. Okay. So if the question may ask you, compared to all of this, which one is better? So the answer will be BPRZ AMI based on this justification, based on the minimum bandwidth, average DC, clock recovery error detection. Okay, because BPRZMI compared to the other line coding format relatively, okay, or similarly, for example, if you want to compare with this with BP with UP with BPRZ, okay, for example, BPRZ require half, okay, bandwidth, so less bandwidth is needed, and it have a comparable clock recoveries, and it able to detect errors. So okay, this is just now is a bit brief, okay, brief. So now the next part is actually we're going to go a bit detail on this format, on the formatting. So this line coding zero, so you have NRZL, NRZM, and NRZS. Okay. So okay, so this you can refer to refer to page 133. Page 133. So you have M, L, and S. Biface M, biface L, biface S. So this one is a bit straightforward, and the comparison for it is given in the page of 134 of the module. Okay, so the non-return to zero is the popular method. It is easy. Data does not return to zero in one clock interval, which I already explained just now. Okay, that's why I touched the name non-return to zero, none. Okay, no synchronization. Can use a start bit for synchronization purposes. Okay, so we have NRZ level. Okay, we have NRZL, and we have NRZM mark, and NRZ is space. Okay, so for the NRZ, 1 is the high level, and 0 will be low level. So you can see this, if you have this as the bits, one binary, 110. So for none return to 0 L, high level will be 1, and the low level will be 0. Okay, this one is not return to 0 regardless of the if you unipolar means you're going to have only one sign, 0 positive or either negative. And if it's bipolar, it's just you're going to have both negative and positive value. But P peak to peak still maintain the same. Okay, regardless unipolar or bipolar. Okay, so non-return 0 marks. Okay, for the bit 1, if you see here for bit 1, it will be a transition at the starting interval, and the non-zero for the no transition. So this one, not sure if you can see clearly. Okay, if you see, I'm not sure you can see it clearly. Okay, for the non-return to zero, for example, for zero, we don't have any transition. Okay, however, if we have one, so we're going to have a transition at the starting of the interval. So this is your NRZ, okay, NRZM. Okay, so there's a bit transition there. And non-return to zero space. Okay, for one, you're going to have no transitions. So it's just zero here. And when zero, you're going to have a transition at the starting interval. So you're going to have a transition at the starting interval for the value of zero. So you see, this is your zero, okay? Zero at the for your NRZS, okay, for your NRZS. So if you see the difference between NRZM and NRZS, it's just that the transition at starting level took place at which at binary bit 1 or binary bit 0. Okay, so okay, let we look again. Okay, sorry for, I think it's a bit confusing just now. Okay, so if you see the transition, okay, sorry, I'm just now a bit mistaken. Okay, so for transition at the starting intervals, okay, for a starting interval, so for the NRZM, so 1, okay, so this is 1, and for 0, no transition, so we just proceed, okay. And after that, for the next one, so we're going to have transition changes, okay. And then for bit 0 is no changes, no transition for the MRZM. And if there is 1, then again the transition changes, and 0 just continue, okay. Sorry, just now I'm a bit I am thinking of something else just now. And then the next non-return to 0 S, okay, space. For 1 will be no transition. For example, we just proceed, and after that 0, you're going to have transitions, and then after that you're going to have for 0, for 1 no transition, so that's why it's just proceed, and for the next 0 you're going to have transition, so 0 here, okay. Change 1 just no transition, proceed, and then 0 is you have transition, okay. And then and so on, okay. So here another 0 will be you're going to have 0 transition. So this one is the RZ unipolar or RZ bipolar. So this one is all side with the all positive or all negative. This one will be we're going to have positive minus. So alternate migration RZ. So RZ is the return to zero at the half bit of the interval. So half bit of interval. So means this is your complete periods. Okay. So half bit of the interval is this one. Okay. And so on. Okay, return to 0 at the half bit of interval, so it must return to 0. Okay, and then overcome by using bipolar signal and alternating paths for synchronization. So we have problem with synchronization, right? Okay, so we can use bipolar signal and alternating paths for synchronization purpose. So for the RZ unipolar, you have 1 as the high level and 0 as low level. This one is pretty straightforward. So 1, so it's just 1 and then return to 0. So this will be your 0 lah. And after that, for the low level, it's just 0. Okay, 0. Then 1, you're going to have up, then return to 0 again. Okay. And then the next one is RZ bipolar. Okay. So you have positive both and negative. So you're going to have, for example, this is your 0. So this will be, for example, negative 2.5. And this will be 5, for example. Not 5, say 2.5 positive. So for bit 1, so 1, then return to 0. And then no changes. Return to 0, and then the same 1 and return to 0. Then for bit 0, we're going to go to the negative level. Okay, and then return to 0. Okay, then 1, return to 0, and then 0, go to the negative digit and return to 0 again. Okay, so for the RZ alternate mark inversion, alternate positive and negative. So we have 1 and the low level. Okay, so MI still here is written. So for 1, okay, I think just now I already showed in previous okay, what is this alternate? So we have alternate or positive and negative. So if the current time it is in the positive, the next representation of bit will be negative. Okay, you see here, this is 1, so it is positive. And the next bit 1 is represented by negative. So this is alternate. Okay, and 0 is always 0 level. Okay, same goes for 1 here. Because previously is negative, so the next one will be positive, and after it will be negative. Okay, one is biphase. Okay, biphase. So used in optical communication system, satellite and video recording. So it have self synchronizing. Okay, so here you have biphase L. Okay, Manchester coding, biphase M and biphase S. So we go to this biphase M first. So biphase M is transition at the middle of the interval. Okay, so you see you have transition at the middle of the interval. This is all middle. Okay, so for the biphase M, you're going to have transition, okay, at the middle. And for the 0, you don't have no transition at the middle of the interval. So new bits start at the opposite level to the current. Okay, new bits start at the opposite level to the current. So you see here, this is bit 1. Okay, so let's say here. So you're going to have transition from low to high. Okay, in the middle of your interval. Then you have the next 1, so you're going to have another transition. Okay, you have another transition from high to low, and then it will going to have transition at the middle of the interval. Here you see new bit, okay, start at the opposite level, okay, to the current. So if you see this is 1, okay, this is 1, this is also 1. However, this is new bit to this one. So it will be started at the opposite level to the previous. Okay, to the previous. And for the bit 1, there will be a transition in the middle. So this is the, what does it mean by this? And then for the 0, so it is another new bit. So that's why you're going to have opposite level. So if this is positive, this will be negative. So opposite level. And because of this is a bit 0, so we don't have transition in the middle of the interval. Okay, and then new bits. Okay, new bits will start at the opposite level. So this one is low, so this one will be, the next one will be high. Okay, and then there will be a transition in the middle of the interval. So next, biphase L, Manchester coding. So transition from high to low at the middle of the interval for bit 1. And then 0 is transition from low to high at the middle of the interval. So this is biphase L. Okay, biphase L. For the 1, we're going to have transition from high to low. So you see here, right? High to low, the middle of the interval. And for the 0 is transition from low to high. So this why you have this. Okay. Used in the internet, high Ethernet IEEE 202.3 standard in LAN cable connection. Okay, this one. Okay. 9 is a biphase S inverse of biphase M. So biphase S is basically the inverse of what you have understand in the biphase M. So this one is just inverse of biphase S. So you can test this concept yourself, practice. Okay, because it's just difference with the transition or no transition. Okay, for in the biphase M, one there is transition. However, in the biphase S, there is no transition. Conversely, for 0. So with that, we finish on this of this chapter, which is the pulse modulations. Okay, so the rest, I hope that you will read detail. You read detail from the module. Okay, so and try to do the exercise in the module. Okay. For those that didn't have module, maybe you can ask from your friend, because I cannot simply share the snap of this module because it's people copyright and the people's effort, and it's not be fair for those that buy the books and the those that didn't buy. Okay, so so happy learning. With that, we finish chapter 4, past modulations. Okay, thank you.